Hello, hello. Here we go again. We are coming up on, well, by which I mean it's in the future for me, in the past for you. Saturday was, I guess I'll use your language. Saturday was the 1 year anniversary of the last day we were fully in person. I'm in the Learning Center recording these videos for you, and I remember the classes I had here then. I am optimistic that things will continue to get better. We have vaccines that are coming through, and things are going to get better. I am looking forward to things getting better. I hope you are too. Please continue to stay safe as we follow that path. All right, we are picking up where we were leaving off last time. Last time we talked about Del Ferro, Tartaglia, Cardano, whoever you want to give credit for. We talked about their solution to the cubic, and I worked through a rather long example, and I came up with an answer at the end, which is a nice thing in contrast to what usually happens. What usually happens is you don't get an answer in the end. So I'm going to probably more quickly, because I'm doing the same thing here as we did last time, but probably more quickly work through the same thing and show you what usually happens with the cubic formula, why it's a problem, and how Bombelli found some ways to work around this problem, which are kind of nice, but kind of sad. And then we'll talk about Ferrari's quartic. And then I have a little bit to talk about what our new material for 6.2. Not much about 6.2 though. All right. So, but lots of things. So let's get going. This is still Cardano, still 1545. I'm not writing it up because it's the same as last time. I want to notice what usually happens. And to do so, I made up this example. And I said, all right, I'm going to do this example because I know the answers. The answers are 1, 2, and 6. Those are the roots, clearly. So I multiplied this out, and I got that. Okay, fine. And then notice that there's a 9 here. So remember, we did this shift last time. And that really is where it is. We didn't talk about it that way, but it really is a horizontal shift. So you're taking all the zeros and shifting them either right or left. But it's, yeah, if we let x equal y plus 3 and put that in for x, then part of that expansion will have a 3 times 3, which will give me a 9, and it'll cancel that 9, and it'll be great. So when we do that, it cleans up as we expect it will. This is actually good news. And we prefer having those negatives on the other side for a couple of reasons, both because of the method that we're using and because we like positives. So this is actually, so far, this is working out pretty nicely. And you think, yeah, this is not going to be bad. The numbers are going to be fine. We're not going to have any problems, and we'll find one of these 3 roots, or maybe more than one of them. That would be really great. How would that happen? Who knows? So the next thing, as we did last time, we let, I'm not sure where to put this, which is why I'm pasting. Anyway, case we let y equal u plus v. We then have on the left side u cubed plus 3uv, u plus v plus v cubed, and the right side we have 7 times u plus v plus 6. And so from that we have this system of equations as we did last time, u cubed plus v cubed equals 6. This is not the only way to do this, but this is a way that would solve these things, and 3uv equals 7. Last time it was nice. This number was a multiple of 3. It's not anymore. That's moderately inconvenient as far as things go. So we're solving the system of equations. V equals 7 over 3u. And then putting that back in here. u cubed plus 7 over 3u cubed equals 6. By the way, it's worth pointing out, this then becomes the 6th degree equation, 27u to the 6 plus 343, which is u cubed, equals 162 u cubed. 343 is 7 cubed. It's worth pointing out this will always be a 6th degree equation at this stage, but it will also always be a quadratic in u. So that part's nice. So we can always solve this equation by using the quadratic formula. And then the same, in fact, we have this issue that u and v are the same. So we get two answers, one's u, one's v. We add them together and go forward. All right, so away we go. We have the quadratic formula. Oh, by the way, seems worth pointing out, long time ago, people knew the quadratic formula. We've been talking about it most of the semester. So of course, by this time, they just use the quadratic formula. They didn't worry about it. Don't you worry about it either. U cubed then equals from the quadratic formula here, 162 plus or minus the square root of, 10,800 negative, oops, 54, which if we clean this up a couple of times, we get 3 plus or minus 10/9 square root of 3. That's u cubed. So y is u plus v, which is happily hanging out right over here. U is then the cube root of one of those. 3 plus 10i. Oh yeah, there's an I here. We would call it I. They, of course, weren't calling it I then. Plus the cube root of the other one. 3 minus 10. Okay. And what you should notice is that's a mess. And it's a weird mess because the answer to this question is either 1, 2, or 6. So somehow all this stuff manages to simplify and become 1, 2, or 6. I honestly don't know which one because I haven't tried to work it out, but that's weird. This is why solving cubics led humans to take complex numbers seriously. Because in a path to find an answer that's either 1, 2, or 6, you find this as the expression for it, and somehow when you simplify it, things cancel magically and you end up maybe with 6. At least there's a 3 here and a 3 here, and we're adding them. You know, it's not quite 3 plus 3, but it seems like it could be related to that. So first of all, yeah, this is not really easy, by which I mean it's almost impossible to simplify this without having some serious guesses as to what's going on. Without knowing the answer in advance, what you would do is you'd say, all right, well, let's move one of them to one side and cube both sides. If you do all that algebra, all you're doing is undoing this work and you'll eventually end up here again, which is kind of funny. I have done that foolishly thinking it would help me once, not in recent years because I learned my lesson. But if you try to start, all right, let's try to simplify this stuff, you end up back exactly with this equation. So that's not very helpful. This form of writing an answer this way is, in the end, not very helpful. All right, let's look at what Bombelli had to say about this. And I will soon show you what Bombelli had to say about it, but I will set the stage a little bit. So Bombelli, working shortly after Cardano, also in Italy, unsurprisingly, was looking at the equation x cubed equals 15x plus 4. because Cardano had looked at the same equation. All right, let me show you something. Let me show you something. All right, hey, it's our course, yay. Come on. All right, and here's Bombelli. And this is Bombelli talking about this actual equation. Notice he says 1, 15, 4. This is what he's using for equals in these times. There's a 3 up there, which tells me it's the third power, and a 1 here and a 0 power. Down here, he has 1 to the third power equals, oh, that we can pretty clearly recognize, 15 to the first plus, using the P for plus. All right, so here's Bombelli doing this work. And he gets an answer, which I will show you soon, and then maybe come back to what happens there. So let me stop this. All right, so Bombelli says use the formula that I will call Daut-Ferro's formula that for solving the cubic, the stuff we've been doing. And when you do that, you get x is the cube root of 2 plus 11 square root of negative 1 plus the cube root of 2 minus 11 square root of negative 1. And one thing that you should definitely notice here, this is the same as the square root of negative 121, the 11 times the square root of negative 1. And I will come back to show you that's not it. That's the weather. Blame the weather. That's what I would do. That's not it at all. All righty. There you go. All right. What we have is this here. Notice that there is this square root of 0 minus 121. So this is the in 2 minus the square root, the cube root here. All right, so here, right here, is that expression. The cube root of 2 plus the square root of negative 121 plus the cube root of 2 minus the square root of, all right, good, good, good. I'm not going to come back to here much more. You can look at it more, but I don't think I'm going to come back there anytime soon. All right. So what Bombelli does, he says, well, how do I make sense out of this? He notices, to start with, that 4 is a root here. 4 cubed is 64. 4 times 15 is 60 plus 4. Oh, so 4 is a root there. Well, that's interesting. And like I was saying in the example I showed you a moment ago, he then hoped, and it really is a hope, he hoped that this would equal 2 times something times the square root of negative 1, and that this one would equal 2 minus something times the square root of negative 1. And the square root of negative 1s, which who knows what they mean, but they would cancel. That's what Bombelli was thinking. And he said, well, can I then get that this cube root of 2 plus this 11 square root of negative 1, can I get that that is, in fact, 2 plus something times the square root of negative 1? So to find out, to check if this happens, Bombelli says, well, all right, let's cube both sides. Let's cube this and see if we can make it equal 2 plus 11 times the square root of negative 1. So we cube this. We get 8 plus 12n times the square root of negative 1 plus 6n squared times the square root of negative 1 squared plus n cubed times the square root of negative 1 cubed. Bombelli then was the first person to have this idea. He said, well, it's the square root of -1. So if it behaves like square roots should, the square root of -1 should just be -1. And the square of the square root of -1 should be -1. And the cube of the square root of -1 should be negative the square root of -1. So he says, well, let's try that out. And this gives me that. Minus 6n squared, the minus coming from squaring that -1, minus n cubed -1. And his goal is to get this to equal, as we said, 2 plus something times the square root of -1. No. 2 plus, his goal is to get it to equal that. 2 plus 11 times the square root of 1. That's something in particular. And notice, if you let, so we have 8 minus 6 times n squared. If n is 1, that gives me 2. And we have 12n minus n cubed. If n is 1, that gives me 11. Hey, this is nice. So Bombelli says, this is great. Apparently, this here equals, in fact, 2 plus the square root of -1. And this here equals, in fact, and he goes through the same work, and I'm not going to because it's exactly the same work and it's rather tedious, 2 minus the square root of -1. Hey, when I add them together, I get 4, which is, in fact, an answer to the original problem. So that is why people at this time started taking complex numbers seriously, because they found out that by doing so, they were allowed to find, or able to find, real answers to numbers with real problems. Real answers to problems with real answers. So that is why humans started caring about complex numbers. Not because anyone ever wanted there to be a square root of -1. There was no real desire. It was easy to just say there was no such thing. But here we see why admitting that there's such thing allows you to do valuable work and find an answer that you thought you could find. All right. What about quartics? You thought solving cubics was a lot of work. Oh, yeah. By the way, the end of the solving quartics will be, oh, and then just solve a cubic, which is not easy, but such it is. All right. This is down here. All right. Oh, I didn't have a code last time, and someone scolded me for it, but I don't have a code every time. But we are about to talk about Ferrari solving quartics. This was actually published in Cardano's work, so I'll put the same date as we did for Cardano of 1545. So the code word for today is sports car. I have no information as to whether this Ferrari is related to the sports car people, but hey, it's a fun code word. All right, that was Bombelli. No, thank you. All right, this is going back to Cardano's work. And at the end of Cardano's book, he says, oh, so here's this problem that my student Ferrari did. And it's presented a little differently here than it was in Suzuki's book. So I do want to call your attention to that. The problem as described here, and I will write on the board as I'm doing it, but then that's probably good enough. But then I will show you the board, so you'll be fine. So the problem as Decoy, who is here called Johannes Kolla, but if you see down below, yes, this is Zuasa Detone Decoy. Tonini, I guess. So, all right, this is the same person. Divide 10 into 3 parts So 10 into 3 parts. So all right, A plus B plus C is 10. In continued proportion. In continued proportion means the ratio of A to B is the ratio of B to C. You don't need to know that, but that is what it means. Such that the first multiplied the second gives 6 as a product. Okay, this problem was proposed by Decoy, who said he could not solve it. I nevertheless said I could solve it, but I didn't know how, which is Cardano, who knows what his problem is. But you are not surprised given everything you know about Cardano. But Ferrari did know how to solve it. And here's some setup. So put then 1 unknown is the middle number. So I'm going to focus all of my attention on B. We will let B be X. And then the first will be, well, all right, that's probably not the way we would write this. But if B is X, then A is 6 over X from that equation. And then the third will be 1/6 of a cube. If we come here, we have AC equals B squared. And we can solve that for C is B squared over A. And B squared is X squared. A is 6 over X, so divided by 6 over X. So we get X cubed over 6. Hence, these together will be equal to 10. So we add all these things up. 6 over X plus X cubed over 6 equals 10. Multiplying all by 6 unknowns, multiplying everything by 6x, we shall have 36 plus 6x squared plus x to the 4th equals 60x. He then says this here as 1/4 power plus 12 squares plus 36 equal, oh wait, no, not there yet. Hence these together, multiplying by all 6 unknowns, we shall have 60 unknowns equal to 1/4 power plus 6 squares plus 36. That is what we have here. I'm going to leave off on this translation. You can come back and look at it if you want. This is where Suzuki picked up. He says Decoy's problem was this. He is not technically right. This is a few steps along the way in Ferrari's solution of Decoy's problem. Decoy's problem is these 3 original equations. 3 numbers, they add to 10 together. They're in continued proportion. The first times the second is 6. That's Decoy's problem, which leads us here. So I don't think Suzuki was misleading us, but some of the expression was a little different. Ferrari was able to solve this, and hence able to solve all quartics. Sort of. Able to solve means to write in terms of radicals and roots of things. As we found, that's oftentimes, by which I mean usually, not very helpful. But he is able to do that, and I guess that's nice. It's worth pointing out also, if we started with a general 4th degree polynomial equation, the first step will be to eliminate the cubic term, just like we eliminated the quadratic term. In this case, we will let y equal x minus a over 4. Let me emphasize that again. Y equals x minus a over 4 instead of 3, because we're now raising things to the 4th power. All right. What I want to talk about and get this whole solving polynomial equations put to sleep for a few centuries, I want to talk about how Ferrari solved this one. And I'm going to try as hard as I can to fit this all on one board, simultaneously show you how you can apply Ferrari's method in general. All right, so I'm going to take away all of this because we don't really care about Decoy's problem at this point. We'll take Suzuki's attitude that this is Decoy's problem. That's close enough. All right, so one version of this is we have 36 plus 6x squared plus x to the 4th equals 60. In general, we have x to the 4th, and I'm not going to write a cubic term because I could use that shifting again to get that to go away. So I will just start with a quadratic term and then a linear term and a constant term. All right. So that's my goal, to solve this equation. And then as I'm solving this, I will show you how one does this in general. All right. So what we want is ideally to make things into squares so we can take square roots to lower the degree. We really do not like the fact that everything is 4th degree. 4th degree is way too high, so we would like to lower that. So what do we do? This is not a perfect square. In fact, it's missing 6x squared here. Notice if we did have x to the 4th plus 12x squared plus 36, then it would be a perfect square. So I'm going to write it in that order now that we're paying attention to such things. So this is a perfect square. In fact, it is x squared plus 6 whole thing squared. I hope you can see that. There's an x here that I almost lost, but I saved it. Here we added 6x squared to the left side. We better do that to the right side also. So x squared plus 6 whole thing squared is 60x plus 6x squared. Let's see how that plays out over here. We're going to move lots of things to the other side. Negative qx plus, no, not plus, but minus r. Great. And we want to make the left side a perfect square. There's several of them we could make, but the one we will choose is 2px squared plus p squared. I hope you see that this will then factor as x squared plus p whole thing squared. The right-hand side, well, what did I do? I added a px squared to make that a 2, and I added a p squared. So there's a px squared and a p squared. So this is negative qx minus r plus px squared plus p squared. All right. So now we're at this stage, both in our particular example and in the general. Now, what we want, we have a perfect square on this side. We'd like this side to also be a perfect square, but it isn't. So what we'll do is add in an extra variable to give us some flexibility, an extra variable we can choose to make whatever we want so that we can make both sides squares. This should remind you of what we did in the cubic where we introduced u plus v instead of just y. Here we will introduce a new variable, we'll call it y, in the place of u plus v, in the place of, anyway. So what we're going to do is look at that, x squared plus 6 plus y whole thing squared. Surely that's a perfect square. And in fact, where it equals is, all right, let's think of it this way. It's x squared plus 6 plus y whole thing squared. So that will give us x squared plus 6 squared plus 2 times this, 2 times y times x squared plus 6 plus y squared. Well, I'm not sure how much I'm running into the other side there, but okay. Oh, but wait. We've seen this before. X squared plus 6 whole thing squared is apparently just equal to 60x plus 6 squared plus 6x squared. 60x plus 6x squared. 2yx plus 6 squared. Notice, by the way, the degree in x just went down by 1, by 2. By 2. Notice this was 4th degree in x, and now this is just quadratic and this is quadratic, so that's interesting. And we can do a tiny bit of algebra, simplifying things, gathering them together. Gathering the x squareds together, we have 6 of them. And we have 2y x squareds over there. We have 60 x's. And we have stuff that doesn't involve x's. We have 12y, right there, 2y times 6, and y squared. So that's the stuff that doesn't involve x's. Let's see what would happen over here on this side if we did the same thing. We'd have x squared plus p plus y whole thing squared is, well, let's see this step by step. The first part is going to be x squared plus p whole thing squared, which we said is this. So that's the first part. And then we have the same thing as we did here. 2 times y times x squared plus p, and then y squared. All right. And then we do algebra over here. By the way, look back at the source. Notice again that none of the people had all this algebra notation that we're using, which is astonishing that they can do all this without having this to keep track of things, but nonetheless. So what we do is gather the x squareds together. We have p plus 2y times x squared, not plus, minus qx, there it is, minus qx, plus p squared minus r plus 2py plus y squared. There's the stuff that doesn't have x in it. All right, fine, fine, fine. Now what? Well, what we want is for both sides to be perfect squares. Because what we really want is to take the square root of both sides. That's what we would really like to do, so that we can lower the degree, and then we'll have something we could solve, because if you see that, the degree over here will be 2, the degree over here will be 1, it'll be a quadratic. We've been solving quadratic equations for a long time. So we want this to be a perfect square. I hope you know, I'm not certain you do, but I hope you know that there's a way to do that. There's a way to tell if a quadratic polynomial is a perfect square, and that way is by looking at the discriminant. That thing from the quadratic equation, the square root of b squared minus 4ac, that thing. If that thing is 0, then the roots repeat, then that's a perfect square. So let's look at the discriminant. We have b squared, which is 60 squared, minus 4a, 6 plus 2y, c, 12y plus y squared, and we want the discriminant to be 0. What happens now? That's a good question. We've made progress, but there's still a vast amount of work to be done, but we're going to stop about here. Ferrari and Cardano, and I guess Ferrari and Cardano and no one else at this point, look at this and say, ah, that's easy, that's a cubic equation. I don't know if they thought it was easy, but nonetheless, it's a cubic equation. Notice if you multiply this whole thing out, the highest power that y is the third power. So what would need to be done at this point to finish this problem? Solve this cubic equation. Find what y is. Put y in here, 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 and here. This side is then a perfect square. This side is also a perfect square because the discriminant made it so. So we can factor this as a square, then take the square root of both sides. Then you have a quadratic equation because there's this x squared on this side and something linear on that side, because it will have an x in it out of this. Then solve that quadratic equation for x. And finally, you have found the answer to this problem. Wow, that's crazy business. By the way, what happens over here in general, the same kind of thing. We were at this step in here. So the next step here is then again to find the discriminant. So that is still b squared, which is q squared minus 4a. Of course, they didn't call these things b squared and q squared and things, but I'm letting us use our language for the discriminant since it's the same idea that they have. And set that equal to 0. Solve that equation for y. And then follow the same process as I outlined over here. Put it back here, here, and there. Take the square root of both sides. Get a quadratic. Solve that for x. And then finally, you have what x is. You have it, but in almost all likelihood, it's in a completely useless form when you've done all of that. All right. So, wow. That's how you solve quartic equations. We could go through all of this and do it with symbols over here and write down a quartic formula. It takes about a page. I'm not exaggerating. It does take about a page. The cubic formula takes about half a page. The quadratic formula you've all known. The quartics were solved soon after cubics. And this led people to be optimistic. Oh, all right, let's keep going. Let's solve quintics. We should be able to do that. And they tried and they failed for a while. We will come back to this story in a few hundred years and find out what's going on. But for now, we've made big progress suddenly. The Babylonians could do quadratics and many others since then that we've talked about. Kayami could do cubics, but he wasn't doing them algebraically. We now have cubics happening in the Italian Renaissance. And shortly after that, we have quartics happening. And then we wonder about what's next. Speaking of wondering about what's next, good. I think this worked out just great. I'm going to come back to our course materials. There we go. So there's more work on this, lots of work. You can look through this. Notice it is not written algebraically. It's a lot of geometrically things. This is all the work that I was just talking through you about. Lots of words, lots and lots of words. Oh, and eventually he comes to an answer, which again is not terribly useful. And so, all right, is getting to be extremely involved algebra. All right, I need to clear the board, so I'm going to do that. While I'm doing that, you can look at the list of things we're about to talk about. The next person I'm going to talk about takes a step backwards in time because, as you know, Suzuki does. He jumps in regions and in time. By the way, the theme music for today is connected to 6/2. So is Germanic music from the time of Johannes Müller, who is also known as Regiomontanus. There he is. Regiomontanus. This is an example of a Latinization of a name. His name was Johannes Müller, sometimes called Johann Müller. He worked in 1463, and he wrote some things about triangles. There he is. We can see someone, which is always a nice thing. All right. Good. So let's look at what he wrote on triangles. I don't know how much I'm going to write things about this. So this is in 1463. This is therefore earlier than what we were just talking about. So that's, I guess, worth noting. So this is introduction, which is not very interesting. This over here, which I will see if I can try to show you. Come on. Why can't you go to that side of the picture? I'm going to pause this and then I will get that to work out for you. All right, I'm not sure what's happening with the computer right now, but I'm going to try to make my way through this. Strange things may happen partway through. Don't let that disturb you. Okay. We'll come back to you seeing this. All right, so this is, there we go, Regiomontanus, and he's doing trigonometry, he's talking about triangles. So this is on Latin. It starts out in every right triangle, and then there's something about acute angles, and there's some other things that we're not sure what they are, and there's this picture. So let's see what the translation is here. For those of you who don't read Latin, which includes me. Here we go. Here's the same thing we're just looking at. In every right triangle, if we describe a circle with center, a vertex of an angle, and a radius, the length of the longest side, then the side subtending this acute angle is the right side. All right, so in this triangle, if we have some acute angle, let's say this one here, then the side subtending that angle is the sine. So BC here is the sine. It's worth noting for them, the sine is a length, not a ratio, in a fixed particular circle. So what, it's a little different than the way we do things. You could say that this is a unit circle, but they did not say that. But aside from that, it's the right idea. The third side is equal to the sine of the complement of the arc. Let me remind you, you know the sine of the complement. You just call it by an abbreviation, which is cosine. So AC is the cosine of this angle. All right, fine. And then he says sort of the same thing again, referring to this particular picture. So if right triangle ABC is given, C is the right angle. Yep, A is an acute angle. Yep. And there's a circle, and BC, opposite angle BAC, is the sine of arc BE. It's interesting they're doing sines of arcs, which is a little different than the way we would think about things, but okay. And AC is equal to the sine of the complement of the arc. So I guess if they're thinking about arcs, they're thinking about that. We would think about that angle. All right, so there's sine and cosine, which is nice. I think, I don't think there's a reason to do, oh, there is some reason to look at this. So theorem 28 here says that working with ratios is actually fine. They weren't. They defined sine and cosine to be lengths, not ratios. But working with ratios would be a fine thing to do, they say here. And, or he says here, I guess this is one person, Johannes Müller, sometimes called Regiomontanus. Then here we have in every rectilinear triangle, that is just a triangle with straight lines in the plane, The ratio of one side to another side is as that of the right sine of the angle opposite one of the sides to the right sine of the angle opposite the other side. This is the law of sines, which is a little bit more difficult for Regiomontanus to prove than it would be for us, because we would just use this length AK and say it's the sine of this angle and it's the sine of this angle. He doesn't quite get to do that because his sines all need to be in the same circle. So he draws a circle over here with the same radius as this circle. So AK is the sine of this angle down here, and DH for him is the sine of this angle down here. And from there, he then uses some similar triangles and reduces to the way we would normally think about these things and proves the law of sines about the way we would. In fact, proving the law of sines is not so terribly difficult because it just amounts to finding this height in two different ways. And that's the way we'd prove it today. That's the way Regiomontanus proved it back then. Nothing very stunning. Let's see if we have anything noteworthy here. There's the words of the proof. It is worth noting here, here's the something noteworthy that I think will wrap us up for today now that I'm having these weird technical difficulties. There's a little bit of spherical trigonometry done here, which maybe involves versine, which is something even stranger. By the way, the versine, if we come back to this picture, the versine of angle A, this angle A here, is this distance up here, GK. That's the versine. It's 1 minus the sine. And it's a trig function that isn't used much anymore. But Mueller refers to it in his spherical trigonometry. Eventually, he ends up with this result here, which is a quite nice looking result for spherical trigonometry. All right. That was an awkward ending. Let's see if I can show you some things that are less awkward. Strange. All right. Christian Rudolph had some new forms of variables that he was looking at, which are kind of interesting, I guess. He said constants would be denoted with this symbol. Variables, the radix again, would be denoted by this symbol. The census, which is the square, would be denoted by this symbol. And then he had all these rules for how he combines these things. He had a table for how to multiply variables. Not so great. He is also responsible for giving us the square root symbol we now use and popularizing Widman's plus or minus. So that's something nice, I guess. Here we get to see someone again. Here's Adam Riese, sometimes called Adam Ries, who is famous for writing books about arithmetic. So famous that apparently people still say in Germany, so you do arithmetic this way because Riese did it this way. Here is a page from Riese's arithmetic in which they were finding information about measuring barrels. If we go back, it says that down here. This page deals with measuring the contents of the barrel. That's what it is, which is a practical thing to want to do. Here is another page from the same thing. This is a translation between numerals in their German word form, Roman numerals, and the still pretty new Hindu Arabic numerals. I don't know if I have a date for this, but I imagine that if I ask nicely enough, they will have a date here. So it looks like Riese was doing this in the 16th century, working in Germany. This is not new creative mathematics. This is expressing arithmetic, primarily, in fact, for children, as was discussed in the text. Here's Stifel's version of the arithmetic triangle, which you look at and say, yeah, we've seen enough versions of that so far. You might think, wow, there's a lot missing, but a lot missing was just repetition. So I think Stifel didn't feel it was necessary to write all that down. And in case you wanted to see Copernicus, at some point you should know what Copernicus looks like. Yes, this is what Copernicus looks like. It's worth noting regarding the solar system that actually we now know, there's something that looks like the solar system. We now know that the sun's also moving. So it's not correct to say that the sun is standing still and the earth is moving around it. So it's not actually wrong to say that any one is the center. The point, however, is that it's a whole lot easier to model the solar system if you put the sun at the center and have things going in circles around it than to try to describe how things go if you were to throw the earth at the center. All right. Wow, that was a lot of things and a somewhat strange ending thanks to some weirdo technical difficulties I still don't understand that I hope never happen again. Thank you for your patience. We will start chapter 7 on Thursday. By the way, chapter 7 is after your exam. The exam covers through chapter 6, so we have now finished all the content that could possibly be used on your exam. I do not want you to talk about any of the people we talk about next on your exam. That's the rule. Okay, thank you very much, and bye.